have any problems with that? Do I need to talk about any of this? Each guy.
Yes, the steradians.
The steradian.
We didn't know how to calculate.
Let's go ahead. So you could probably already calculate the intensity, right? That's the watts divided by 10 centimeters squared. And you have to remember, convert centimeters squared into meters. And hopefully you will do that correct. I know some people mess up. The way I do it is I would do it like this. I'd say 10 centimeters squared. And then inside that I can write, that would be 0.1 meters squared like that. And that's the way I usually do those conversions to make sure I get those right. And then of course, or if you want to be really, you really should go inside the notation here. 10 to the minus 1 meters equals 10 to the minus 2 meters squared. Okay, this one is not very right.
Isn't it 1 to the negative 1 meters?
10 centimeters, yeah, you can write 1 to the negative 1, but if they're squaring and stuff isn't going to make a difference. If I had like 30 centimeters, then yes, I'd have to write like 3 times 10 to the negative 1. Be careful about it. Okay. So that would be your area, so you're dividing your 30 watts by 10 to the minus 2 meters squared. So you end up with your 3 times 10 to the 4th watts per meter squared. Okay.
Wait, no, it's not. It's to the negative 3.
Oh, you know
That's
what?
what I was saying.
I did it wrong.
It's 1
You're
to the
right.
negative 1.
You're absolutely right. It's 10, I have to get the parentheses in the right place. I had the parentheses wrong. And then we're going to get 10 times 10 to the minus 1 centimeter squared. And then, yeah, we end up with 10 to the minus
To the negative, to the negative 2 meters.
minus 2. Yeah, 10 to the minus 2 times 10.
Oh, okay.
The 10 to the minus 1.
No. It's 10 times 10 to the minus 2 meters squared.
Yeah.
Yeah.
There we go. And then we end up with 10, that's correct, 10 to the minus 3. Okay. There we go. Yeah.
I had a question. So in the when they were looking at like the different wavelengths,
Yes.
like it pinpointed it. Like let's say you wanted to look at it at 0.5,
Yeah.
and they took it between 4.45 and 0.55.
Yeah.
And then I was wondering, like, I know that I realized you just have to take the difference in the range,
Yes.
but like, how does that? So I tried to do it at first by looking at the very like midpoint between those two, and I got a different answer.
Well, no, if you do 0.4 plus or minus 1 not 0.4, 0.45 plus or minus 0.15 microns.
Oh, okay, plus or minus.
Yeah.
Oh, okay.
Then, I mean, you're still going to have the range of 0.3 microns is the range. But 0.3, then, it's a very good point. It's centered around 0.45 microns.
So if they were to like, if the question was like posited as, what's the spectral range, then would we do that? Or is it still the same?
Yeah, I mean, you really just have to look at how they're wording it. But the range that matters, and if they care to give you what the central point is, I mean, in this case, the central point didn't matter. But yes, you would probably call it at 0.45 microns. So, the other area, so of course, you're going to say intensity is equal to let's do power per area. So we're going to have our 30 watts divided by 10 to the minus 3 meters squared, 3 times 10 to the first watts over 10 to the minus 3, 3 times 10 to the fourth watts per meter squared. Okay, now we had a question about radiance and spectral radiance and stuff like that. Spectral intensity are divided by the wavelength range, right? Radiance, the way that we are defining radiance is going to be equal to the intensity divided by the change in the solid angle. Okay? But then we have to figure out what the solid angle is. So we're dealing with something where we have 20 centimeters away and looking at an area of 10 centimeters squared. Okay? So that thing there is your angle. Now, you could write it, you may be confused to say, oh, what, is it angle or is it changing an angle? It's an opening in an angle, but delta omega there. So, whether you write it delta omega or this omega, I'm going to write it delta omega here. It's going to be equal to the area over radius squared. And then we can decide how we want to play around units here. But they should all cancel out if you do everything right. If you do it over the centimeters. So I can go ahead and write 10 centimeters squared divided by 20 centimeters. But then you have to square that whole thing. Okay? So then we're going to end up with 10 over 400 or 0.05 times 10 to the negative 2. Okay? And that's why you're going to be dividing by. And then we're going to take our intensity up there, we say 3 times 10 to the 4th watts per meter squared divided by 2.5 times 10 to the negative 2. There are no units, so the units cancel out. Your powers of 10, so we have 3 over 2.5 times 10 to the 6 watt per meter squared. And we often just keep writing dividing lines there. Otherwise, you're putting like dashes underneath and stuff like that. Okay? And then you clear out 3 over 2.5. So 1.25 there. Anyway, that's how that's done. Or 1.2. Okay. And then spectral radiance, you're just dividing with it by the wavelength radius. Okay. So, yeah. The change in the wavelength. Yes. It's the wavelength range. You're not doing positive or negative.
So, the spectral radiance, the radiance divided by the changing wavelength.
Yes.
And also, the spectral intensity is the same intensity divided by the changing wavelength.
Yeah. The way in the literature, as I said, well, I'm calling spectral radiance in the literature, but it's going to call it radiance. I'm just putting spectral radiance in there to think, oh, I have to divide by radiance, and I have to divide by wavelength. This is spectral. Any other questions? Should put these in stuff. Yes. Okay. And expected ratings, you just divide the ratings by the change.
Okay, so the radius is 20 centimeters.
Wait, the radius is...
The radius.
Oh, radius is 20 centimeters, yes.
So we don't have to use the 10 where the circle is.
Say that again?
We didn't have to use the 10 where the circle was.
Oh, that's the area. It's not this radius, it's the radius to the source of light. So yeah, there's more than one radius here, but draw that as a square, you may be less confused. But yeah, when we talk about radius, we're talking about this distance from the point source of light to the observer. Okay? Good point. Make sure you know which radius you're talking about. Okay? Now, going on here, this is really to get you thinking. What happens to a beam light as it passes through a medium? What would happen to if we make the particles in the medium larger, keep the same number of particles, but we make them more larger? What's going to happen to the scattered light or the reflected light?
So if you look at the phase scatter function, so most of the light will scatter parallel to the entry beam, and the least amount of light will scatter normal to the entry beam. And then you will also have some reflection in the opposite direction.
Okay, you're going the next step. I want you to go one step before that. Do I have more or less light being?
Less.
You're saying there's going to be less light.
Well, actually,
I say the denser the medium, the more opacity, opaqueness it has. So there will be less light. Opacity.
Yeah, but let's make this really simple. If I have a bunch of particles there and I just make each particle bigger, what happens to the chance that that's going to interact with the light? It gets higher. So what's going to happen to the amount of scattering, and probably going to cause it reflection here, probably going to cause it scattering. What's happening to the amount of scattering?
Increase.
It would increase, right? What would probably happen to the amount of absorption if these particles happen to be absorbing? More highs, more absorption, right? Larger particles is going to be more absorption. Yeah. How about I make more particles? What's going to happen to scattering and absorption? More of them, okay? By the way, what's happening to the optical depth each time?
It's increasing.
It's increasing. Anytime absorption or scattering increases, the optical depth is increasing. Okay? And of course, if I made them, let's say I have the same particles and I make them more transparent. More transmission, so how about absorption? Less absorption. How about scattering?
Less.
It could be the same. It could be the same amount of scattering. What they're doing is they're like adding some dyeing there so that maybe it's not going to absorb it. Now, the question is, if you come and do multiple scattering, you may end up with less multiple scattering because there's more of a chance of it being absorbed. Oh, well, if you want to say there's less scattering, if you say it's being absorbed instead of scattered, you could probably say that. How about if I made the particles larger but more transparent? What might happen to the optical depth? What? Okay, so we have less. Yeah. How about the total optical depth? Less optical depth, right? Might increase because of the scatter by making it more transparent. Yeah.
transparency favors a lower optical depth.
Yes, but I also made it larger.
Okay, so it's absorbing more, but it's still transmitting through.
Yes.
Yeah.
It still increases because the interaction with the particle increases.
You're okay. You guys are all correct. I did not give you a yes or no answer here because it turns out maybe you make everything bigger so there's more interactions, except that it's more transparent, so there's less absorption. You could have no change in optical depth if you do it just right. Or it could become larger, it could become smaller. Depends on the balance between what you've done with, larger particles and less absorption, stuff like that. So you get to the point where you actually have to calculate everything out. You see, the optical depth is total scattering, total absorption. Okay? So I do want to get your homework so I can begin to learn your names and stuff like that. So you do have them, right? Have them. You can email it to me. Email it to me if you don't have something you can't. Any other questions about this before we go on? Yeah, look at fun. A whole bunch of stuff and scattering, absorption, and scattering into the beam and emission and stuff like that. Today we start to make your life simple. Two things that we're going to try to ignore are multiple scattering and emission. Now, right, do this. But let's be very clear what we're going to be talking about. We're going to be talking about a direct beam only. That's the coming. So here I have light coming through a material and it's taking a detector. But light can also be scattering, which means I can get light scattering off the material, and some of that scattered light may hit the detector. We don't want to be dealing with that. So what we can do is you make a collimated detector, and then a lot of the light would come and hit the detector, be captured by the collimator, as being absorbing collimator there. So you're only getting a direct beam. Now a real collimator would be much more narrow and skinnier than this. If we are actually going to get some scattering in detectors. But that's the basic idea. Yes.
I have a question. What if the walls of the collimator have like a reflector to take in more?
Then they're not helping.
So it would make it more confusing to like.
Yeah, you need absorbing. Okay. So remember, I was looking at collimated light. Now your eyes actually do collimation because they're lenses, and lenses are very selective about direction. So if you're looking up a cloud and you see the sun coming through a cloud, if you can see the shape of the sun, you're looking pretty much at the direct beam of the sun. But there's a lot of other light coming to your eye there too. That may be because your eye is not a perfect collimator, but also can be because of what we call multiple scattering. So, let's first see what we're going to try to simplify. We had this basic concept, changing intensity, absorption, scatter, takes out. Wait, this beam is it didn't take the timing off. Okay. So, we're trying to get rid of the scattering and the absorption so that we only end up with this equation here. Okay? Now, I may have to go and take off the timing there, but we don't care about most of this other light. We only care about light that gets scattered out and then gets scattered in the same direction. If it ends up in the same direction, we can't tell it apart from that beam. So that's the multiple scattering that we want to get rid of. So how do we get rid of that? Well, if the number of scatters is small, remember it has to scatter twice. It scatters out of the beam and then it scatters forward. So if we don't have many scatterers, the chance of it happening twice is much smaller. And kind of the probability squared here. Now the scattered cross-section particle is small. So if you have like very small particles that don't scatter very much, or if they're highly absorbing, if they tend to absorb rather than scatter, then that second scattering is less likely. So we really want to maybe be looking probably at absorbing materials if it has a thick optical depth. If it's small optical depth, then we just want to make sure that it's pretty small optical depth so you don't get the multiple scattering. Okay? Now we also want to ignore thermal emission. So this is the solar spectrum way up there. Turns out that we are also emitting. This would be terrestrial temperature emission over here. Now this is much smaller. And there's a little bit of overlap there. And we have our visible, we have the near IR, which we don't see. But then we also have this little overlapping area here, which we want to avoid. Okay? So we have the thermal IR, but we stay out of that region of less than 10 microns or so. Let's think about 5, I'd say let's think about 5 microns, 3 to 5 microns. then we're avoiding the mid-infrared region. Okay? So this is what we spend a lot of time doing. We're trying to keep the wavelength smaller than about 3 microns. You can ignore thermal emission. Okay? That makes sense? I'm going to stop the timing here because that's going to drive me crazy. Okay, so as long as we're in this part of the spectrum, as long as you're out the thermal part of the spectrum, we don't have to worry about things glowing extra light through our detector. Whatever we're worried about is the direct beam that's being scattered or absorbed out of the ray. Okay, done with that. Maybe IR? With IR, people try to avoid, you can't do it. If you know the temperature of something, you can calculate how much emission it would do and you can correct for it. But sometimes, for example, if you're looking at thick clouds, you know that you can get a pretty good temperature of that cloud. You say, okay, I'm going to have some emission from that cloud, so I can subtract that out, everything else is reflection. However, if you have a thin cloud, you may not know how much the cloud is emitting versus how much is coming through from underneath and stuff. It becomes more complicated. So if you're working in this crossover region there, you have to make sure that you really do know the temperature of the optical things are optical thick and stuff like that.
Because the cloud is symmetric to a certain temperature, it needs to be so.
Yes. They would both emit, but those are reflecting. There's a little bit of solar radiation left there that can be reflected. So if you're looking at a wavelength thing there, you might think it's both emission and reflection. So you have to either know one or the other in order. So we are going to avoid that region here. Some people do things where they do use that region, but you have to be careful.
And the second one is just the emission of flushing due to the temperature. Not that it would be the temperature or reflection that the emission.
Okay, we have the thermal stuff depends on the medium and on the temperature. The reflected stuff depends on, of course, the amount of sunlight coming in and then the medium. Okay. When we get into this, I'm first. So right now, we're just going to say if you're in a wavelength smaller than 3 microns, we can ignore what this thermal stuff is. Unless you're around a bonfire or something. The most terrestrial temperatures don't produce light smaller than about 3 wavelengths.
So most likely happen when the wavelength is small.
The proportion of scattering thermal increases. I'm not going to say there's more scattering, I'm going to say there's less thermal, which means the proportion increases. But don't think of it as you're increasing scattering, think of it as you're decreasing the thermal. Okay, so let's go back to our equation here. We have that. We can kind of rearrange it algebraically. And then we have this thing, and what is that thing going to turn into? Most of this. What's this and what is that? That's our optical depth. Okay? Remember, optical depth is measured in the vertical direction. So if you're going in a off vertical, you're cutting through more material. That's where the cosine comes. So we only measure optical depth in the vertical. Okay? So far so good. So now let's go back to our equation there. So we're looking at light that's being removed from the direct beam. This was our whole big equation. Then we divide it by optical depth, so we end up with our optical depth over here. We can get rid of Well, if that, so long as we have, pure absorption or we have very thin medium, if not scattering much. So all of that's going to go away and we end up with this guy. That guy we can deal with. That guy we can manage. Okay? So if you integrate that, and I think you can all integrate it, this is what we end up with. We end up with this exponential function. Okay? And this is known as Beer's law, named after Mr. Beer, who derived it. And we're going to be spending the rest of the day really just talking about this. It's not good enough just to give you an equation. I want to make sure you have a very deep understanding of it. So, first of all, when we have the absorption and the scattering, we put them all together. Alpha plus sigma, absorption the scattering coefficient, or just called the scattering coefficient. So we've really simplified it down to a coefficient times the density times how much you go through the version. Okay. Let's see how this thing comes about. So, first of all, we can have our median here broken up. We have 50% of our median here and 50% of our median down there. If we have a total optical depth of 1, so we have everything nicely organized, any light that gets caught by the first half is going to get caught by the second half. You're going to end up with nothing coming through. So in a perfectly organized world, an optical depth of 1 means everything is, all the light is being intercepted. There's no direct beam left. Do we live in such a world? No, we do not. We live in a world that looks more like this. We have half of it here and half of it there, but it's kind of random now. So, yes, half of it will get through the first part, but then the second half is going to capture half of the remainder. It's random. So instead of getting 0 coming through, we get 25% coming through. Now, I broke this up into 2 layers. Of course, we have to go differential calculus and break it up into 1,000 layers each one. And if you do that, you're actually going to end up with more like 37%. Okay? Even though if you organize everything perfectly, it would all get caught. But that's not the way the world works. There is randomness. So, in order to demonstrate this again, I need to clear off space here on my board. You guys ever seen a overhead projector before? Yeah. There used to be oiler range, the way everybody, showed lectures and stuff like that. But now that we have PowerPoint and projectors, nobody does it anymore. However, they're still really useful for demonstrations. So I'm glad that we have one. And let me dry it off. Because what we are going to do is use paper as optical depth. We're going to kind of recreate what I just did there. So, if you could hit the lights. Right now, I have a sheet of paper, nice organized sheet of paper. Let me get this out the way I want. This should have an optical depth of 1, it's blocking all the light that goes through. Okay? That's an organized optical depth of 1. Now I'm going to disorganize it. The way that things come in nature, I'm going to cut it actually into 9 pieces here. That is into 3. And we're going to pretend that every piece here is equal in size. Okay. So I have 9 pieces of paper. I'm going to put down, a third of the pieces of paper in random there. I've done an optical depth of 1/3. How much light is coming through? 2%. 2/3, right? 2/3 of the light is coming through. It's an optical depth of 1/3. But as I continue to put down pieces at random, what begins to happen? So now I have 2/3. Now, does that mean 1/3 of the light is getting through? No. Why not? Well, not even scattering. Tell you what, it would help if one of you would kind of stand up and look down at the projector. They're overlapping. We are getting overlap, which means instead of 1/3 of the light getting through, more than 1/3 of the light gets through because of the overlap and makes bigger gaps. In fact, if I keep adding paper here, I'm going to go up to an optical depth of 1 here. There's an optical depth of 1. You say, well, the light blocked. No. A lot of light is still getting through because of overlap. I could cut up another piece of paper, put an optical depth of 2, and light would still be coming through. Okay? Because of the random nature of reality here. There are always going to be gaps. So, an optical depth of 1 means that if we did everything just right, all the light would be blocked. But that doesn't happen. We have to get more probabilistic things. Okay? So really what you're doing is, if I have an area here, an optical depth of 1 should be able to fill up the entire area with all the cross-sections. If I was using marbles, it'd be the cross-sectional area of all the marbles would fill up that area. Okay? Get this back up. But when will we be coming back to this? No, we have the lights back on. Oh, it's just dead then. Okay. Now, we're going to derive exponential decay, and you can do it by integration. But integration is a trick. Most of you, how many of you have done numerical integration? Have you ever done it? Yeah. Numerical integration is real. The integration you get taught in calculus is more of a trick. Sometimes it will work, sometimes you can't do it. The numerical integration is actually a better way to approach things conceptually to understand what's going on. So we're going to kind of do a numerical integration. Is that a question?
Use something like Simpson's rule.
Use a what?
Like Simpson's rule.
Not even that complicated. I would say if you're doing numerical integration for understanding, you're not doing one of this fancy stuff. You're just saying, well, let's do it. Let's do it here. Okay? So here I have light coming through a substance. I have the original light, and then I have the first bit of light that comes through a little fractional slice detail. I'm going to be adding more slices detail as we go on. Okay? So, of course, the changing intensity is just, what comes through minus what we had initially. Okay? And how do we figure out how much comes through? From what we just did, it should be the original amount of light times the optical thickness that we went through. Look at that for a bit and make sure it makes sense. We had an optical thickness of 0.1, how much does it change the light?
10%.
And it's going to change it by 10%. Whatever the original is, if the optical depth is 0.1, it's going to eliminate about 10% of the light, right? That was before things began to overlap. We have to be talking about very small optical depths. So if I put like one ninth of a piece of paper on there, 1/9 of the light is being intercepted. Okay?
So I naught is the optical depth.
No, I naught is the intensity. Sorry, this is intensity. I naught times optical depth will tell you how much to change the intensity. Yeah. It can be anything you want. It can be 30, it can be 1,000. The question is how much of a change is making a fractional change in the original intensity. So the amount of light that it loses, let's say the amount of light is 1,000 watts per meter squared. If I have an optical depth here of 0.1, 100 watts per meter squared is going to be how much we change the light cost. So if I end up with 1,000, I go to an optical depth of 0.1, what do I end up with? 900. 900. The change is 1. Okay. How about if I had an optical depth of 0.01? 999.
Oh, yeah.
Yeah, stuff like that. Well, 990. 990. It's 10 stuff like that. Okay. So the optical depth is telling you, so long as it's small, and believe it's small, the optical depth is telling you what fractional change you make in the intensity. Okay. That clear with everyone? But we're not done. Because this was only delta tau. This isn't the entire optical depth. We're going to have to go through this again. But before we do that, that means what is I1? It's going to be the original intensity times 1 minus this optical depth. So if the optical depth was like 0.2, how much gets through? 80% gets through. Okay? Stop for a little while, make sure everybody gets it there. No, optical depth can be in the hundreds. Because remember, if I kept putting paper in there, if I put another sheet of paper, light would still get through. We can keep adding optical depth and it would die away exponentially. When I keep adding optical depth, the total optical depth increases the intensity. The transmitted intensity. Not how easy. How easy it is for the stuff to be blocked. How much is being blocked? The optical depth is the amount of stuff that blocks the light. Right. Right. But because it's not going to be a linear block, it's because it's random. So if you have an optical depth of 0.2, then you have to do 0.9 comes through times 0.9 goes through the next one. So dying away yeah, in an ideal world, an optical depth of 1 would mean nothing comes through. You have 0.
No, it's because you said I1. That's why I'm saying.
No. An optical depth of 1 in an ideal world would mean everything is blocked. Yes. Yeah. But we don't live in that ideal world, so a fraction will. Okay. So that's the first one. We all have a comfort level with that one. Yeah, that's done. So we have now, we're going to go through another little sliver of optical depth. Now what's going to happen?
Same thing.
Same thing is going to happen. We're going to have to do I1, not do I0. So I2 is equal to I1 that's 1 minus delta optical depth, which means we're going to 1 minus delta optical depth squared. Looking through the next one. Okay? So remember, if this is blocking 10%, that optical depth is 0.1, this is being multiplied by 0.9.
So
now we're multiplying by 0.9 twice.
Assuming you have the same optical.
Yeah. So, yeah, if it's the same optical depth. So, by the way, why is 0.9 squared? 0.81. If everything was organized, you say 0.2, 0.2, and 0.1, 0.1, 0.2, we say it would be 18%, but now we're at 81% being transmitted. A little bit more is being transmitted than it's just being organized. Okay. Here we go again. That's cubed, okay? So we're just applying the same thing over and over again.
That's nice.
Okay? By the way, That's an exponent, right? We came up with an exponent before. If you do the calculus trick, we came up with the exponential, an e to some power. Then I have to relate those two things together. So, first of all, does this whole thing make sense now? You can look and say, oh, I'm going to get the original optical depth, 1 minus each of these slivers is going to take away a certain amount if I have to raise to the power. 90%, 90%, 90%, so on. Okay. So, if we want to know what the total optical depth is, we're going to go through a bunch of these. It's going to be n times delta tau. So, the nth intensity after it goes through n of these is going to be this thing raised to the nth power. Or I could rewrite it like this if I want. Okay? Now we're going to play a little mathematical trick here. So, I mean, that's kind of our final equation there. Notice that raised to the power tau. Then we have this one. So the question is, as you take delta optical depth very smaller, which means n becomes larger, of course, what is this thing going to end up becoming? Okay, so let's make it a little bit simpler. I'm going to rewrite 1 over the tau as m, so that this thing becomes I0 times 1 minus 1 over m to the nth power, raised to the tau. Oh, I'm having a problem with the boiling power point versus mean power. That's weird. Okay. Well, kind of what we can do here. That's going to be,
They're just brackets.
yeah, they're just bracket. You're right. It's just a bracket. Okay. How come I get that bracket and don't get this bracket? Okay.
That's the concept.
And this is saying that I is going to, and that's b e to the minus tau. Huh. But this is going to work. What I want you guys to do here is we have a number in here. It's a limit as m goes to infinity. Now here we have 1 minus m to the m. I'm going to change it. Let's do 1 plus 1 over m to the m. So I want all of you who have a calculator, go ahead and put m is equal to 1 in this equation when you begin. In fact, you don't even need a calculator for that. We're going to get 2. Now take m, call m equal to 10 when you begin.
10th power.
2.1
to the 10th power.
2.1 to the 10th power, take 2.1 to the 10th power. No, it's actually 1.1 to the 10th power. 1.1 to the 10th power. There we get 2. What you get when you take it to the 10th power?
2.59.
2.59. What happens if you take it up to the 100th power?
You get 2.70.
0.70. Oh, let's do one more.
You get 2.72.
2.7. Do you see where this is going?
Yeah, it's
F goes to infinity, we're going to get E. 2.1, 2.71, that is the exponential. Okay? So that's what the successive going through a bunch of little slivers would give us. Now, here I had you a positive. What happens if you get a negative? You're going to get 1 over E. Okay? Or e to the minus 1. So this is going to end up giving you e to the minus 1, which means that has to be a tau there. That equation that we had before Beer's law, we can get it by going through this process.
So the model is a logarithmic curve.
Yeah. Logarithm. Okay. I'm upset with that. I need to fix that. infinity. Yeah, as m goes to infinity, this thing is going to go to e to the minus 1. If this is e to the minus 1, it's going to become I0 e to the minus tau. So now that we've derived this, that's e to the minus tau. Great. Right, it doesn't have any of my equations here, does it? Oh, this sucks. So as tau goes to n times, delta tau there, we're going to end up with this equation that we had before, even though it's not right. And eventually we're going to end up getting the same equation that we had before, but here's one. Okay? So that's where Beer's law comes from. Just applying the same thing over and over. So now that we have Beer's law, let's see, do I want to do this? Mu is cosine theta. Okay? So that adjusts for the idea that you're not going straight down, you're going on an angle. So the optical depth is what is measured vertically. You go up here, you're going through optical depth divided by cosine theta. Okay.
Excuse me,
Yes?
can you please share the screen so that we can track better in which slide you're at?
Oh, man.
Okay, thank you.
Okay, yeah, that would be worth sharing, but sorry about that.
Yeah. The email.
Great.
I'll sharing.
Okay, so, yes.
So you're the beams that are you're basically using cosine theta to realign it
I'm
vertically.
using cosine theta to take a path that would be a certain distance if we're going straight down, turning into a longer distance.
Oh, you want to turn it into a longer distance.
Yes.
Okay.
So effectively, what's happening is if you're coming in at an angle, if you're coming straight in, cosine theta b could be 1. So if we're coming in like this, we are, where's my equation? We're dividing by cosine theta. You're ending up getting a longer path length. So as though you're increasing the optical depth. In fact, you are increasing the optical depth in the direction that we're going. Okay? Optical depth is measured vertically. If we're not going in the vertical, you still say you have the optical depth, but you're going through more material if you're going out an angle.
Okay, so the idea is that it's not what's happening, but you have to consider the fact that we have a angle.
Yes.
Yesterday, I want to know why yesterday you considered you kept perpendicular to the plane.
It's
And
the same.
today you went into the.
No, we were talking about the same thing yesterday. The idea is if I have the sun straight overhead, I'm going to have the intensity. If I'm looking at something over there, I'm going to measure a lower intensity because it's going through more material. But we don't want to say, oh, the atmosphere has a different optical depth just because I'm looking in a different direction. We want to say it's the same optical depth, I'm just going through in a different direction. Okay? So that's the key idea there. You got it? Same optical depth, different direction, you actually have more light that's being affected. Okay? So, let's go ahead and see if it works. Do you remember this setup? Now this time, you might notice I have put a collimator on this detector here. Because remember, we're only talking about collimated light now. And because we're talking about Beer's law, we have to have some kind of thing. This is a root beer. In the past, I have used a nice dark beer. That stuff's pretty pungent. I end up smelling like a frat movie. So we're going to go ahead and use root beer here. And you can see what we have going on with here. Do we have our, which one of these are we going to be interested in if we're looking for the transmission?
Blue first. Red.
I think that one. That's coming through the water from above. Okay, so we're going to be keeping our eye on that one. And I'm going to go ahead and start adding some here. So right now, first we want to keep this one. So we're going to connect. Wait. I want to make sure I have everything set right here. Okay, connect. Oh, I need my 10-second average. There. How about it stay? Okay. So, here's our first one we're collecting. And 0 here. Okay, so we have 150. Let's put 150. Yeah. Oh, I'm not happy. Have to go back to the. There. This is going to be the transmitted intensity. 0, we have about 150. 150.5. Okay? Now, of course, I need to add some. I'm actually going to add 3 of these because this is kind of light here. And what do we expect to happen to the transmitted light? It could decrease. It could go down. Or that could happen. Okay. A much higher, oh wait, it's still pretty high. I guess it just had it lined up better. You got it? Yeah, let it restart. Yeah. So when it was uncollimated, it was up in the 400s. Now I put the collimator on. You lose a lot of light coming in from the edges, and that can mess things up. So I'm going to keep this one. Yeah, I have some light there. Okay, so this time we have about 210.9. I'm going to call it 211. Okay. Now I'm going to add 3 measures up here, or I'm going to call it 1 here. By the way, what should happen to? We know what's going to happen to the transmitted light. What do you think is going to happen to the reflected light? We'd expect less reflectors. Okay? I'm going to grab that one and grab this one.
It's gonna decrease.
Did it decrease?
transparency.
It's like looking at a burning pond, you see your image better.
We have about
Okay.
160, 68, 67.
We're going to call that mixing in one. Okay. Rescale. Okay. So now we went down to about 167. Okay. Well, yeah, but I have to take the one that averaged. That looks like it's settled down to here. Maybe I averaged too soon.
Yeah.
Yeah, I averaged too soon in it. Well, yeah, let's write down 170 then. But that's much more stable. Okay. Now, if I was to predict what this would be, what should I do if Beer's law is correct?
Take the percentage and
Percentage, or take the ratio. Try taking the ratio. What is the ratio of 170 to 210?
0.81.
Okay. Ratio.
So 1 to 0.8.
Okay. You can predict what the next one would be. Meanwhile, I'm going to add the Beer here for Beer's law.
You're gonna create a low. You're gonna create a middle.
130.
Now here it becomes tricky. I could see very clearly when the milk was not well mixed. It's a lot harder to see when the root beer is not well mixed. And it's going to stir around here for a while.
Second.
Looks okay. Keep that on. Okay. So what do we get now? 143. And what's the ratio of those two?
84.
Okay, 0.84. Let's do one more. You know, this is about the same. Do
Yeah.
okay. I can only do one more because I'm going to run out of beer. And to be honest, because of the foam and this stuff, this is not being measured perfectly. So we do expect some noise in the data. Okay. Nicely. Not bouncing around too badly. Okay, so we've got probably 123. What do we get for a ratio there?
26.
0.86? Okay, well, it's moving around, you know, like I said, not measuring too much, but you see we're getting about the same ratios every time.
Yes.
So if I could get everything measured perfectly, it should come out much better than this. Okay? So that's the idea of Beer's law. But of course there we weren't using exponentials. We weren't using the e to the whatever. So now we need to work on using e to the proper power there.
Professor, if I may ask, which part of the PLO do they use the ratio? I didn't see it in the paper. I thought it's just the equation that it's talking.
Yeah, when we were deriving it, we were kind of using ratios here. We were multiplying by the same number. We were multiplying by 1 minus tau. Like here, we're multiplying by 1 minus tau each time. So what we're saying is, if this is a ratio, what would tau be? The little bit of tau that I'm adding. About 0.19. Okay? So I'm adding an optical depth of about 0.19 there, which means that the ratio is 0.81. How much would change the original?
So this formula, the ratio, what is starting to,
E will come out once you do a bunch of them. You have to add up all of your taus and stuff like that. The connection is in the limit.
the 0.81 is the.
Well, what I could do here, I would write that I1 over I0 is equal to e to the minus tau. Okay? And then you solve for tau. You solve for tau, it's not going to be exactly 0.19. It's going to be a little bit different. But it's approximately going to be 0.19.
So this is exponent minus tau that we are calculating.
Yes.
It's not tau.
It's not tau, yeah.
Okay, I just want to make sure.
Yeah. I mean, this is going to be approximately equal to 1 minus tau if tau is small. E to the minus tau is approximately 1 minus tau if tau is small. Okay? So if you're using small optical depths, it's often better to use this rather than that, because that is easier to think about and use. Okay? By the way, look at how the reflection was dropping as predicted. Get rid of that. Let's see how many more equations we have messed up.
No.
So, this equation here where all of this thing is actually tau, we can write as an extinction coefficient. So if you solve for the extinction coefficient, we're talking about alpha plus sigma, the absorption plus the scattering coefficient, the extinction coefficient. Now if you look at it, if you look at the real density, this is going to be the amount of stuff times z is the amount of stuff per area. This has to be unitless, so it turns out the k has to be an area to make everything work out. So
the summation of the scatter and the absorption is an area, or is it unitless?
it comes out to be the same unit as an area, or area per amount of stuff. It depends on how you're measuring the stuff. It's going to become like area per cc of root beer or something like that. The units come out the same as area. So we often refer to the coefficient there, the extinction coefficient, as the cross-section of the material. Because it's like a cross-sectional area. Okay? So if you're able to talk with people and say, oh yeah, the cross-section of this is so much, they're talking about like the area per molecule, the equivalent area per molecule. The equivalent area per, kilogram of stuff that you throw in there, stuff like that. Okay? And it's going to change with wavelength, it's going to change, but it's like an area, a cross-sectional area. Okay? So in this cross-sectional area, the absorption goes as the electronic structure, where you have electrons being bumped around and light hits it and being absorbed. the scattering is going to be related to the geometry and the index of refraction, stuff like that. So they're very different things. Okay, so here we're just talking about what happens if you want to figure out what the coefficients are. So we can rewrite Beer's law as, let's say you know the density of the material, you know how thick it is, you want to figure out what the cross-sectional area is, you can just go ahead and you can solve it. So rho dc is the amount of stuff that you have, and then you're just multiplying by the extinction, which you can measure in the laboratory. So if you've measured this in the laboratory, and maybe you're trying to find that, then the changes in light will tell you how you are getting, how much material you have. So let's go ahead and try this.
Is there a correlation between how much material you have and the layers of it? Like,
Yeah.
Is that how you use?
That's why it is.
So, okay.
If you're integrating rho dc, what is integration?
The area.
Adding up all of the layers. So dz is like that every layer with a certain density, and you add up a bunch of layers here. And eventually, if you multiply by the cross-section, you get the optical depth through all of these layers. Okay. So, all of this is going to be swimming around in your head unless you actually do it. So let's actually do it. So we have a photodetector pointing through a pan of water. Doesn't that look familiar? And we're looking at a single light at an angle of 60 degrees at the vertices. It kind of goes off to the side. You read an intensity originally of 120 watts per stereo per meter squared. But then we add some T there. T is absorbing, right? Absorption is good for Beer's law. If there's too much scattering, we may have other effects coming in. So absorption is a good thing. We add 5 cc's of T to a liter of water, the intensity drops to 90 watts per stereo. And we have a direction that's very collimated like what I had there. So the first question is, what is the optical depth of the T? So how would we figure out the optical depth of the T? Yes?
We look at the ratio of the initial from the final.
We could do that. That's kind of what we're doing. That works for small optical depths.
That's very small.
This may, yeah, that one works for, well, actually it works for anything, but then you have to start using the exponential.
We have an angle now.
Yeah, we have an angle in all of that.
Yeah.
Okay?
Okay.
So what will always work is Beer's law. So we are going to use Beer's law here. There's Beer's law, by the way, and that has to have first cosine theta. You know what? It seems like once you start wiping with a paper towel, you always have to use a paper towel. I'm going to leave that. Get rid of this stuff. So, if we're looking at this equation here, do you see a way to get optical depth from the information that we have? Yeah, go ahead and do it. Oh, and by the way, let me yell at you now so I don't have to yell at you later. How many of you are tempted to just plug in all of these numbers and then solve for optical depth? Don't do that. Solve symbolically for optical depth and then plug in your numbers. The reason for that, if all of you don't do that, you probably know the reason for that. It's much easier to catch an algebra problem than it is to catch an arithmetic problem with all of these numbers running around. No, but that doesn't have to be, it's cosine of theta. Once you stick in the cosine function, it doesn't care what you have. What do you end up with for your optical?
0.144.
Something like that. Okay. By the way, why did I not bother to put units in there? They're the same things, they're gonna cancel out. If it weren't that, it'd be very bad in me not to put units in there, because you have to make sure you get everything canceling out or you're in trouble. Okay, so we have the optical depth of the T. The next one is if the amount of T is doubled, what would be the transmitted intensity? There's actually two ways you can do this. Yeah.
We say, I think the optical depth is delta tau, right?
We were using delta tau when we were deriving the equation from taking little slithers of optical depth. Now that we're looking at the entire amount of optical depth, it's no longer delta tau, it's just tau.
So we're using delta tau when we deriving the equation, or
And what we were doing before, we were working with very small amount of optical depth. And we would say things like that amount transmitted is 1 minus, a small amount of optical depth. That works then, but once you begin to get to larger optical depths, you can't just say 1 minus delta tau is the ratio of light transmittance.
and then we just consider tau.
Now in this case, it turns out the total tau 0.144, that's small enough you could probably say e to the minus tau is equal to 1 minus tau. You'd probably get about the same thing. But be careful about doing that. Once optical depth becomes larger, you can't say 1 minus tau is the same as e to the minus tau. However, ratios can still work out.
Is there a direct relationship between the optical depth and the amount of T? Like, does doubling it, half it?
Yes. The optical depth is directly related to the amount of T. But if you double the amount of T, what do you do to the optical depth?
No, you double it.
You double it.
'Cause it's more
Optical depth
absorption.
goes to the amount of stuff. You diminish the transmission by increasing the optical depth.
Wait, then the optical depth is how much is like reflected back. So how is it cut?
Oh, it was, for small optical depth, yeah, the optical depth is how much might be reflected back. But what happens to the transmission as you have more reflected backwards? You have less transmission.
Then we're talking about transmission.
Yes. Beer's law is talking about transmission. As optical depth increases, transmission will go down.
Yeah. When you add the T, transmission diminishes.
Yes.
Okay.
And optical depth is increasing.
Yeah. I'll check out.
Okay, so on the next one, the amount of T is doubled. What would be the transmitted intensity? There's two ways of doing this.
We do,
One way,
we have to find I squared. That's just
you could do
I
that.
two, sorry. So we have to use the deriving exponential to decay. Where it's I squared equals I1, or the original intensity
1 minus delta tau squared.
Okay, so let's do method 1 here. And this is actually not using Beer's law. You're going to say for how much did they put in there? For 5 cc's of T, I1 over I0 is equal to 90 watts per meter squared per steradian divided by 120 watts per meter squared per steradian, which is equal to 3/4, right? And then you would say plus 5 cc's T. We could say that I2 over I1 should be equal to the same 3/4. Does that make sense? That's what we did over there. Is that what you were talking about, more or less?
Yeah, sort of.
Sure. Okay. So then we have that I2 is equal to I1 times 3/4, or is equal to I0 times 3/4 squared. And we do, what's 3/4 of 90?
67.5.
Yeah. 67.5 watts per meter squared per steradian. That's one way of doing it, but we didn't use this equation. We want to go back and try this equation and see if we get the same thing?
Sure.
Let's go back and do that equation.
But doubling the,
You have to double
By
tau.
doubling the optical depth,
yeah.
okay?
Tau times
So I'm going to use that kind of notation. I'm going to say that I2 is going to be equal to the e to the
minus
is equal to e I0 times e to the minus 2 times tau over cosine theta. Does that make sense? I've added twice as much.
so negative 0.28.
120 watts per meter squared per steradian. E to the minus, now I'm going to say 2 times 0.144 divided by cosine of 60, 0.5, yeah. And if you do all of that, you know what you end up getting?
Same thing.
67.5 watts per meter squared per steradian. Okay? Now, you may wonder, when do I use this one and when do I use that one? This one only works if you're using the same amount over and over again, which isn't completely realistic in the real world. If I said, oh, now I'm going to add 7.3 cc's, if drive yourself crazy trying to do it that way, Beer's law always works. Okay? So this may be more intuitive. This always works. Okay? And then the final thing, this is getting back to coefficients and so on. What is the ratio of T to optical depth? Well, let's say at 5 cc's of T, what was our optical depth? 0.144. Okay? So now you can just do your little division there. You get something like 35.
34.72.
Yeah. 34.7. 34.7 cc's. I'm just going to write it as tau. Tau has no units. But for every unit of optical depth, I have to add 34.7 cc's to get 1 unit of optical depth. Okay. If I could convert that into a density, then I can say, oh, there's a coefficient in front of it. I say coefficient times the density. So, yes.
So the amount is directly proportional to the optical.
The optical depth is directly proportional to the amount of stuff. Okay. However, there's a coefficient there. If I go to a different wavelength, it's going to be a different amount of stuff for optical depth. If I go from T to root beer, it's going to be a different amount. That's where that coefficient comes in. That's where I say tau is equal to integral of K rho dz. I may have the same density of root beer and T, but the coefficient is going to change. So I'm going to end up with a different number. Okay? So far, so good. I know you did your questions get resolved?
I understand the calculation. It's the concept that I'm trying to get when we talk sometimes about optical depth and transmission. I want to know what you're looking for when you say that when they double the T, I know the transmission will diminish. But then not the probability, but the amount of light that has been back up after that stage, at this stage, it's like where it is, where it is. So obviously when you add the T, at the, when you're going to have it at the second time, when you add the T, obviously less than what you're going to get with this. But then I want to have a separate explanation, difference between optical depth and the transmitted light. That's what I'm saying.
Well,
sometimes you talk about delta tau, I understand because it's by layer, but so the interval in out. But then I want to have a separate notion about transmitting and the way to optical depth.
Okay, this will always give you the ratio between optical depth and transmission. Okay, but that's a little bit complicated. It's like exponential and stuff like that. If you have small optical depths, this becomes 1 minus the tau. And let's not even worry about the cosine theta for now. If you have very small optical depth, then you say the transmission is 1 minus the optical depth. That fraction of transmission is 1 minus the optical depth. If you have an optical depth of 0.05, 95% would be transmitted. Once you get to an optical depth of like 0.6, you can't really use this anymore. You have to go back to using the exponential. Okay? So, I think it's good to have both of them in your heads. You think that, oh, as I'm adding optical depth, I'm intercepting more light. The optical depth is the amount of light that's being intercepted, and then it's the total minus the intercepted light. But because it's random and stuff, it becomes more complicated. That's why we have to go to the exponential. Okay? Good enough? Am I running low on time here? Yeah. Maybe. Good. Okay. How about if we have a bunch of different materials? Like I have tea and root beer mixed together. Oh, that'd be good for us. Try that sometime. But what happens if we're mixing together tea and root beer? What happens to the optical depth? Let's say I have tea that has an optical depth of 0.3, and root beer of an optical depth of 0.5. What would be the total optical depth?
You just add it or no? You can't just add it.
We're just adding them.
Oh, you just have it.
They just add. You're adding more material, the optical depth just adds up. That's why we like to talk about optical depth. Now, if you're calculating intensities, then of course you go and do this. So we have our optical depths are just adding up as they add together more stuff. So it keeps it very simple. However, look at the math here. I have optical depth after all added up. I can split it up like this. Now, each of these things say, oh, I'm going to have a certain ratio of intensity coming through. Like maybe the T is going to let, 30% of it through. Maybe the root beer is going to let 80% of it through. Then you end up multiplying those transmitted lights. So this is the transmission. Beer's law is really giving you the amount of transmittance. It's the term that we call it. So as optical depths add up, transmission multiplies. Okay? The optical depth is additive, transmission is multiplicative. So if the T lets 1/3 of the light through and the root beer lets 1/2 of the light through, how much light eventually gets through?
20%?
No. You added, you can add up the optical depths, but what happens to the amount of that optical depth that's through? It multiplies. So it'd be 1/3 times 1/2 is 1/6. 1/6 of the light would get through.
So less than 20%.
Now, yes, less than 20%. Now, you may have a total optical depth of, what was it, 1/3, 0.33, that's 8 plus 1/2 is 0.5, 0.833 is the optical depth. That optical depth will let through 1/6 of the light. Okay? So, if you think of it as just, if I make the T in one layer and everything that gets through the T has to now go through the root beer, then whatever gets through here gets multiplied by whatever the root beer is doing. So you just multiply as you add up the optical depths. Makes sense. Some of you are nodding your heads, some of you are not sure. Okay. Do you need another example of that? Let's do a quick example of that. Seriously, we have, let me run out of time here. Stick with T and root beer. Stick with T and root beer. T has optical depth of, I'm going to change my number here, 0.2. Root beer has optical depth of 0.4. How much does T or root beer transmit alone? How much is transmitted together? Okay? Now, how do you calculate how much each of them transmits alone? Just go like that, okay? So, in fact, I say much, I say what fraction does T or root beer transmit alone? So calculate each of those fractions very quickly. And because I didn't give you an angle, what angle do you think you're going to use? Coming straight in an angle of 0. So you can just ignore the cosine. Anytime you're not giving information, just assume the simplicity. Okay? How much is being transmitted by T?
So T is going to be 0.81.
0.81. How much does beer transmit?
The beer is going to be 0.67.
0.67. Now, both.
0.545.
0.81 times 0.67, 0. What was it?
Oh, actually,
0.54.
0.54, okay.
So we
But
can't,
there's another way we can do it. We could also do e to the minus 0.2 plus 0.4.
oh, so you add them, not multiply them.
Well, here I'm multiplying both of those, or here I add the exponent, the optical depth.
Okay.
Because what do I get? 0.54. Mathematically, they're the same thing.
Yeah, just exponent, yeah.
Does that clarify things a little bit? Okay. Now, life in the real world does be complicated. So here we have transmission through the atmosphere. This is kind of the scattering spectrum. Scattering is geometrical, kind of nice and smooth. Absorption has to do with the electronic transitions. So you get these, very sharp absorption lines here. So let's say that we wanted to measure the amount of absorption in the water, lying right there. The amount that's going to be coming through. Because as the water changes, this amount of absorption is going to change. So you can figure out how much water there is by how deep that absorption line is. But there's a problem. We're not starting at complete transmittance. The atmosphere is already scattering some of that light. And how do we deal with that problem? Maybe we know how much is scattering, but in many cases you don't. If it's a pure atmosphere, we already have that calculated, we know. If it's not a pure atmosphere, there's aerosols and pollution wandering around, we may have an unknown amount of atmospheric scattering we can tell. So what we do is something called the split window technique. You measure very close to what the absorption is. This is going to be your scattering. And then once you know that, then you can subtract out what's going on here with the absorption. Yes?
What about if you use like pure atmosphere as your initial, and then compared it with the
Well,
actual
pure atmosphere would work if you didn't have other stuff in there, honestly.
No, I'm saying using the other stuff as the second point, like not your initial. So like using a theoretical pure atmosphere as your I0,
Yeah.
and then your I1 is what you initially see from the get-go.
That's kind of what we're going to be doing here in a sense, except that doing the pure atmosphere, we already have some unknown stuff in there. We're talking with no point doing
The
that.
pure atmosphere would have.
And it's going to be there anyway, and then it's going to be added to the other unknown. So you just roll them all up together in one big unknown there. Okay. So we're going to pick one. We have our scattering nearby. Now what we can do is we can interpolate in between. I mean, we can measure how much light is being transmitted here and there. We can interpolate how much light should be coming through there if there were no absorption.
Yeah.
Okay? Does that make sense? Okay? So we're just going to figure out how much is going to be going from there. What happened? How do I get back? Oh no, it won't even let.
Try to like, yeah, do the pinch it and
Double
Now-
tap. Double tap on the screen.
Try a horizontal pinch.
Hold your hand down.
No.
trying to send it to the center of the screen.
Try a wider motion pinching.
Yeah.
Ah,
Or just press escape.
I think I just pressed escape. What about you have to go back to the keyboard? There we go. Okay. So we could figure out what the optical depths were here and interpolate to what it is there. And then you're just subtracting out that optical depth. Okay? So because we can figure out the optical depth here, we can figure out there, we can just do it by subtraction. So this, you're not going to completely understand until we do it, so guess what? We're going to have to do it. This is something called the split window technique. It intensities all the time in remote sensing, where if you're trying to measure absorption in one place, you measure right next to the absorption and say, that will tell me how much I need to correct. How come everybody's taking pictures? Don't you have them in your handout?
No.
Wait, that one's not there?
No. The last one was multiple effects.
Yeah.
Oh, did you run out?
There are more
That's weird.
slides.
Okay, there must have been when I made copies, there's a sheet that didn't get copied. Ah, okay. I'll have to get that to you. Well, let's go ahead and do it. So, you have a photometer measures the intensity of 1200 watts per meter squared, yada, yada, yada. Let's draw it out here. So what it's describing is really the same situation that I just had for you up on the board. So I'm going to kind of redraw that. We have something that goes like this, and then there's an absorption like that, right? Now, we have a couple of wavelengths. We have a 0.86 microns. We have 1.1 microns. And we want to figure out what is going on here, which is eventually going to be 0.94. 0.94. Okay? Now, we have a couple of intensities here. So we have an intensity here of 1200 watts per meter squared. Over here we have an intensity of 1050 watts per meter squared. These both have no absorption here. The question is, what would be the expected intensity right here at 0.94 microns? So how would I figure that out? If I know that intensity of 0.86 microns, I know the intensity of 1.1 microns, how do I figure out what I would expect to get a 0.94 microns?
Set up ratios.
Yeah, set up a ratio. 0.94, okay, what's the difference between 0.86 and 1.1?
0.15. Oh, sorry.
0.24.
0.24. That is the delta of wavelength, 0.24, between these two columns. Where is 0.94 in there? Well, we have here, we have delta wavelength is 0.8. Here we have 0.16. 0.94 is 1/3 of the way through, you see. Okay? So we expect the intensities to change about 1/3 of the way. If we go from 1200 to 1050, how much does the intensity change? 150. What's 1/3 of 150? 50. So we have 1200 here. What would you expect here?
1150.
1150. 1150 watts per meter squared. Okay? That's what we would expect if no absorption. So, with no absorption, expect 1050 watts per meter squared Western radian at 0.94 microns. Yes?
Can you explain how you got that again?
Okay. The wavelength 0.94 is 1/3 of the way between 0.86 and 1.1. Good with that?
Yep.
We expect the intensity to be 1/3 of the way. So from 1200 to 1050, the change in intensity is 150. 1/3 of the way is 50. So 1200 minus 50 is 1150.
Is there a better method to do this?
Yeah, I mean, you could separate it, but believe me, once you start writing a little bit down, it becomes even more complicated. So if you can get it by just looking at it in your head, I'm happy with that. You can work out with the detailed algebra later. But yes, there are more mathematical ways to do it. I think it just lose you. It would be like, you know, a couple of linear equations and putting them together. It's not as much fun. So if we can get it quickly, we got it. Okay, so we expected 1050. What did we actually measure? I mean, we expect, sorry, not 1050, 1150. We expected 1150. So that's what we would expect, 1150. But we measured 3. Wait, that's it? That's not, yeah,
That's absurd.
no. That should have been 300s. I don't know why we have a 3 there. Okay, let's change that to 300s.
Oh, but it isn't any good.
What?
There is another way to
What?
There is another way to farm the same result.
Yeah, but still, if we started with 1050, dropped all the way to 3 is kind of crazy. I think it was supposed to be 300s. I don't know why this PowerPoint is messed up. Okay, let's call it 300. So if you want from 1150 down to 300, what would be the optical depth? You guys know how to do this, right? Yes, use Beard's law.
1200 though.
Oh, from 1150. No, 11.
From 1150, we dropped to 300.
So we're using 1150 as our initial.
Yes.
Even though it was predicted.
Yeah, well, that came from these things. They're saying when we have 1150, there's no absorption.
Oh,
So
okay.
this drop is purely due to absorption, not to the other scattering that was going on. Okay.
Your question is to find the optical depth.
Yeah, trying to find the optical depth. And by the way, remember we have about 30 degrees there. But if you have 301.16, probably sounds about right to me.
1.16?
Yeah, I don't know what number I had instead of that 3 that gave me 0.56. So I'm going to go with the 1.56. 1.16. Okay. So, knowing the optical depth of water, and if you know the properties of water in that wavelength, you can figure out the total amount of water. So really, if you have the extinction coefficient for water at that wavelength, you can invert it and go ahead and you can get the density from the optical depth. Okay? And remember, tau is going to be equal to something like rho z times k. So if you know the k from the laboratory, you can get the column density. Okay? And that's how we actually measure the amount of water vapor in the air on a day-to-day basis, the total column, not down there at the surface, but the total amount of water vapor. That's how we can measure it by satellite and stuff. Okay. So, that's really just what we did here. We kind of said, oh, we know what these other optical depths are by measuring the light that is coming through, and then we can separate it out. So, you guys are running out of time. I'm kind of going to rush through here, but this is what was going on. We just kind of subtracted out that when we were dealing with the water infrastructure. Okay? But what happens if you don't know what the optical depth of the atmosphere is? And what happens if you don't know what the sunlight is above the atmosphere? Could we do any of this if we knew what was going on above the atmosphere? Because remember, this is what we knew would be happening if there was no atmosphere. So, tell you what, we're going to skip this. We don't have time to do this. I'm going to go on to this. If you're trying to find the optical depth of the atmosphere, and you're trying to find how bright the sun is, before we had satellites, we didn't really know how bright the sun was. You would think. But we did know how bright the sun was, even though we weren't above the atmosphere. And the way we did it was by this trick called Langley regression. And what you do is, you look at the sun from a number of different angles here. And we know, as I said, we're going to call the optical depth the same, just the path is changing. And when people do this, they redefine m1 over cosine theta as the optical mass. The idea is if you're looking up directly, you're looking at optical mass of 1. If you go at 60 degrees, you actually have going through twice as much atmosphere, like an optical mass of 2, and so on. Okay? Does that make sense?
So there's going to be a
So we're going to assume the atmosphere has a constant optical depth. And of course, we're going to assume the sun has a constant intensity. So we take our Beer's law there. We have rewritten it with 1 over cosine theta as m. You can take the logarithm of both sides. We've been measuring intensity at the surface at all of these different optical depths. You get a straight line.
But you said, what if we don't have the intensity?
We still don't have the intensity. No, we have the intensity at the surface. We don't have the intensity of the sun.
Okay.
But can we get the intensity of the sun? Yes, we can. Because the slope is going to give you the optical depth. The intercept is the log of the intensity of the sun.
So the angle you said when it's vertical, it was 1.
Yeah.
And the atmosphere was,
You're looking through one atmosphere.
and then the
vertical.
angle was 2.
If you go through like 60 degrees, you're going through twice as much atmosphere.
So you're using that.
Yes.
So you're using twice as much atmosphere when
Yeah.
you're calculating.
Yes.
Okay.
You're looking through twice as much atmosphere at the same sun, but you know how you're getting the different amount of atmosphere. So it's a very clever technique here. You get both the intensity of the sun above the atmosphere and the optical depth of the atmosphere. Way back in 1900, we knew how bright the sun was and we knew what the optical depth of the atmosphere was without ever having to fly through the atmosphere.
What were they using to measure the intensity on the surface?
Sun photometer. Even the way that it measures the energy of the light, back then, this is before the photoelectric effect, we were probably doing heat. How much the light would actually heat up the metal. After the photoelectric effect, of course, you use the photoelectric effect. That would have come in, early after 1900.
Wasn't that was
Einstein.
Einstein's time, right?
Yeah.
He was the one who got the.
Yes, he got the Nobel Prize for photoelectric effect, not
Not
for
relativity.
relativity. So that's the way that how we know here. So now we have a homework problem. We all know about sunburn. We all know ozone protects us from sunburn. Typical summer day in New York, sun may reach a zenith that's 20 degrees from the meridian. 21 watts per meter squared of UVB are measured as zenith on the surface. If you have the above atmosphere 35 watts per meter squared are present, what is the optical depth of the ozone? And yes, I gave you the answer. What angle would be necessary for a fairly harmless intensity of 5 per meter squared to be present? I think what I can do, Janet, if I email this to you, can you email it to them? Okay. Because somehow the last page didn't get to them. Okay. So, any questions about this? What? Yeah, you can take a picture. This is gonna email it to you, but if you want to take a picture
I
now.
can print
go
it and
ahead.
bring it
Yeah.
to them. Okay? As soon as I go to my office, I'll print it.
So that whole thing was really one equation, Beer's law, plus permutation where you can do successive ratios will give you the same answer as Beer's law. Yeah. You don't have to. You can. Not that you have to, but that you can. Because 1 minus tau is easier to work with something than e to the minus tau. At least it's easier to think about. Go ahead and play around with it yourself. Go use tau is equal to 0.1, 0.2, and 0.3, and do 1 minus tau, do e to the minus tau. And see how they begin to diverge. And then it's up to you how much are you willing, how much inaccuracy are you willing to tolerate.
Would you like to